I am Wang, and for now I'm a postdoc at Yale University and also a member of the FinAI community. So today I like to share my our recent work in auditing a financial taxonomy structure multi-document benchmark for evaluating LLMs with everyone here. So. I will start this presentation with the following four parts. The first part is background. Uh, at the beginning, I want to give some preliminary knowledge with the following two questions. What is XBRL and what problem does it solve? In shortly, the traditional financial reports, such as a PDF or Excel version, are the just for the human. Well, the XBRL is a financial reporting language for machines. So in traditional reports, numbers are just values embedded in tables with surrounding text. Humans can read them, but a machine cannot reliably understand what those numbers represent. This leads to inconsistent labeling of the same financial concept across no, the different companies or even across the tables in the same document. Uh, so that makes automatic validation, such as checking calculations or reporting correctness, is almost impossible. Uh, XBRL just changed this by making every number self-describing. Each value is explicitly linked to its financial concept, reporting context, and logical relationships to other values. As a result, financial statements become not only readable by humans, but also machine understandable, computable, and auditable. This figure just show the key distinction between human readable and the machine readable financial reports. On the top, highlighted with the red, are the traditional filing documents such as HTML or text files. They are designed for human to read, but they mainly contain narrative text and tables without explicit semantics. The part highlighted in blue are the XBL data files. This includes the instance document and multiple link bases, which explicitly encode concepts, hierarchies, and calculations rules. So while both describe the same financial statements, the top one is for human consumption, but the bottom is what enables machines to interpret, compute, and audit financial data automatically. Since I just mentioned the traditional XBR files include the instant document and six link-based document. So here I want to show what the exactly six documents are in the XBR filings. The first is a instance document, contains the actual financial numbers reported by company with enough context for machines to read and verify them. The second is schema document. It defines the financial concepts used in the report and their basic meaning. The calculation link base specifies how numbers should be added or subtract to form totals. Presentation link base controls how financial statements are organized and displayed. The definition link base defines valid relationships and dimension rules between concepts. The last one is a labeling base, which provides human readable names for concepts for easier understanding. We will now see the six documents that store and organize financial data in XBRL, but none of them actually decide what the rules are. Those rules come from an external taxonomy like US GAAP, which defines what concepts exist and how they are supposed to work together. So this figure just show how to like transform the traditional human readable financial statement to the machine readable XBRL format. In general, converting a traditional financial report in PDF or Excel into a standard compliant XBRL filing involves four stages. The first is the financial statements are created in human readable formats, such as which machines cannot reason over. Second is the tagging. Tagging just maps reported numbers to US GAAP concepts and produce the XBRL filing format. However, a critical misconception is that tagging equals correctness. Tagging only guaranteeing that valid labels are used. It doesn't mean that calculations are correct or that the structure follows US GAAP rules. As a result, many XBRL filings appears standardized but are logical flawed, which makes auditing essential. In the next slide, I will show how these structural errors translate into real-world restatements over time. Um, Um, okay, this figure just show we just look at these figures. You can see there are two lines here. The dark blue line represents the share of reissuance restatements. The white blue line just shows the revision restatements. Over the time, we see a clear divergence. Revision restatements steadily decline. However, the reissuance restatements increased from around 20% to over 30%. Since reissuance restatements usually indicate a deeper structure or semantic issues, this trend suggests that errors in XBRL filings are becoming more complex rather than simpler. Building on this challenge, recent progress in large language models has sparked interest in automating many financial tasks, from information extraction to question answering and forecasting. However, it is still unclear whether current LLMs can support professional financial auditing, which requires consistent reasoning over structured, hierarchical, and interdependent disclosures. Existing benchmarks actually in figure not figures show these tables. We can see there are largely existing benchmarks focused on isolated text or surface level evaluation, and rarely test the reasoning over financial taxonomy like US GAAP. As a result, we still lack a strict taxonomy-grounded benchmark to evaluate whether LLMs can truly reason about real-world financial reporting errors. To address these limitations, we introduce FinAuditing, the first real-world benchmark to evaluating LLM's auditing and compliance capabilities on structured, hierarchical, and multi-document XBR filings grounded in US GAAP. The benchmark defines three core tasks: FinSM, FinRE, and FinMR, uh, covering semantic understanding, hierarchical reasoning, and multi-step numerical verification. Using a unified evaluation framework, we benchmark 13 LLMs in zero-shot settings and found that even shorter models struggle with cross-document consistency about tax and taxonomy-aligned reasoning. Uh, this figure just give an overview of the fin auditing framework. We take the real XBRL findings with the US-GAAP taxonomy as structured inputs and design three uh, auditing tasks. The FinSM focuses on semantic matching and concept retrieval. FinRE evaluates hierarchical and relational reasoning. Third one is FinMR, which tests multi-step numerical verification across documents. These tasks are evaluated across multiple LLMs using task-specific metrics, providing a unified view of how well models support end-to-end financial auditing. At a high level, our task formulate task takes an XBRL filing composed of multiple interconnected XBRL documents together with the US GAAP taxonomy as a structured reference knowledge. The goal is to enable LLM to reason over the internal structure and semantic of these documents and identify different types of errors including semantic mismatching, incorrect relationships, and numerical inconsistencies. In essence, we frame financial auditing as a structured reasoning problem, just given an XBRL findings and its taxonomy. The model must detect and describe where the finding violates accounting logic and standards. The first task is a financial semantic matching, short as FinSM. This task evaluates whether LLM can correctly identify semantically inconsistent and or incorrect US GAAP text in the XBRL filings. Given the financial query and XBRL filing, the US GAAP taxonomy, the model must retrieve relevant concepts and filter raw tags that do not semantically align with the intent financial meaning. Essentially, FinSM tests whether the model understands what a financial concept truly represents rather than just matching surface level labels. The center task is a financial relationship extraction, or FinRE. It evaluates whether LLMs can reason about hierarchical and compositional relationships between financial concepts in XBRL filings. Uh, s- uh, Especially, the model must identify three types of the relationship errors. Just as shown in this the prompt template, we can see the reversal, uh, inappropriateness, and combination error. Uh, the reversal just is parent-child roles are flipped. Inappropriateness represents two concepts are linked but should not be related. Combination errors means the aggregation relationships are incorrectly formed. FinRE, therefore, the FinRE just tests whether models truly understand taxonomy-defined structure rather than just recognizing related terms. A third one is financial mathematical reasoning, or FinMR. It evaluates whether LLMs can verify numerical consistency and compliance in XBRL filings by reasoning over calculation hierarchies and constraints. Uh, uh, Concurrently, we ask two linked questions. First one is the model extracts the reported value of the target financial elements from the instance document. Second one is it computes the value that should be reported based on the calculation relationships and US GAAP taxonomy. The output contains both numbers, enabling us to directly detect calculation and consistency errors. For the data collection, we focus on real-world XBRL filings from official US regulatory source. In total, we collect 372 filings from 2020 to 2024. We first perform a large-scale screening using the XBRL US data quality site, retrieving over 4,500 error messages linked to B2C rules. These errors cover more than 100 Unicode tabs and natural fall into three categories: semantic, relational, and calculation. We then filter for representative and frequent cases, selecting 1,102 errors and extracting 218 matched findings from the SEC database. This process ensures the FinAuditing is grounded in realistic, high-impact auditing errors. The first step of data annotation is data segmentation. We decompose each XBR file into structured subfilings based on a statement level organization, such as balance sheets or cash flow statements. To do this, we identify statement IDs from the schema, recover the corresponding hierarchical structure from the presentation link base, and then link it to other link bases and instance documents. This results in a coherent structure, preserving subfilings that significantly reduce the input length and improve both data manageability and LLM processing efficiency. The second anti-step use LLM-based judgment to automatically construct labels for all three tasks. Each XBR findings is retrieved using the XBR URLs provided in official error messages, which precisely specify incorrect elements, invalid relationships, and unexpected corrections. Using GPT-4o Mini, we generate task-specific annotations. For FinSM, we extract incorrect concepts as ground truth and retrieve the corresponding subfilings. For FinRE, we map DQC rules to three, you can see three relation tabs. Basically, we just use these three DQC IDs to get the relevant error tabs, three relation error tabs. For the FinMR, okay, I forgot mention one. After we get the three relation tabs, we will convert it to the triplet, like the head relation tail. This structure as our input format, is our output format. For FinMR, the mathematical reasoning task, we extract both reported value and expected value and formulate the numerical reasoning question with the relevant context. This process enables scalable, consistent, and rule-grounded annotation across all tasks. The final annotation step focuses on US-GAAP taxonomy trunking. To support structure and fine-grained access, we divide the official taxonomy into concept-centric trunks. We construct two types of trunks. One is a core trunk, which capture intrinsic concept attributes. The other is relation trunks, which encode hierarchical and calculation dependencies. This representation preserves the integrity of the taxonomy while enabling efficient concept level retrieval and reasoning across all fin auditing tasks. We evaluate LLMs on fin auditing using task-specific metrics that reflect different types of structure reasoning. For FinSM, we use retrieval metrics such as hit rate, recall, and macro F1 to measure whether correct concepts appear in the top-ranked results. For FinRE, we report accuracy and macro average precision, recall, and F1 to fairly evaluate classification across different relation types. For FinMR, we go beyond the accuracy and introduce error rate that separate the extraction, structural, and calculation mistakes, allowing us to uh, pinpoint where numerical reasoning fails. Uh, Here is the model we use to evaluate our benchmark. Basically, we are using 13 models here, such as one general closed model LLM, 10 general open source LLMs, and two domain specific financial LLMs. This table reports hit rate and key for the FinSM task under zero shot settings. Each row corresponds to an LLM, and the columns show whether at least one correct US GAAP concept appears in the top key retrieval results. Overall, performance is consistently low. Even the strongest models achieve average hit rate of only around 10%, while many models fail to retrieve any correct concept at all. Increasing K provides only marginal improvement. These results indicate that fine-grained financial semantic matching remains a major bottleneck, suggesting that current LLMs struggle to accurately align financial concepts with US GAAP semantics in realist auditing scenarios. This table reports required key for the SM task, measuring how many of the incorrect US GAAP tags a model can retrieve within a top key results. Across all models, record remains consistently low, even as key increases. This means that model may occasionally retrieve a correct concept, but they fail to comprehensively cover all semantic mismatches in the filing. Together with the hit rate results, this shows that current LLMs lack both precision and coverage in fine-grained financial semantic retrieval, especially when reasoning across interrelated financial documents. This table reports macro F1 and K for the FinSM task, which strongly capture both precision and recall across all mismatched US GAAP tags. We observed extremely low macro F1 scores across all models, even for the strongest models, the DeepSeek V3. Um, uh, this indicates that models struggle to balance accuracy and coverage when retrieving semantic incorrect tags. Taken together with hit rate and recall, these results show that fine-grained financial semantic retrieval remains fundamentally unsolved, especially in structured taxonomy-grounded auditing settings. Next one is the table just summarize the overall performance on the FinRE task, reporting accuracy and macro averaged precision record and F1 across three relation tabs. Overall, the relationship extraction from structured XBRL filings remains challenging for most models, LLMs. Among all models, GPT-4o achieved the best balance between precision and record, reaching around 90% macro F1, while performance drops substantially for other models. These results suggest that correctly reasoning over taxonomy-defined financial relationships is still difficult, and strong performance requires robust structural understanding rather than surface-level pattern matching. This figure breaks down FinRE performance by individual relation types, such as reversal, inappropriateness, and combination error. We observe large performance uh, differences across relation types. Most model perform relatively better on reversal errors, which involves simpler parameter chat flips. In contrast, combination error is consistently the most challenging, as it requires precise hierarchical and aggregation reasoning across concepts. Overall, this analysis showed that many LLMs still lack robust structure alignment with accounting taxonomies, especially for complex compositional relationships. They figure just show the performance of the last tasks FinMR. Overall, performance is extremely low across all models with most accuracy remaining below 10%. This indicates that LLMs struggle with the full pipeline of extracting a reported value, computing the correct values, and verifying numerical consistency within hierarchical XBRL filings. Even strong models fail to reliably perform this kind of structured mathematical reasoning, uh, highlighting FinMR as the most challenged auditing task in our benchmark. This figure breaks down FinMR errors into three categories, as I mentioned before, which is structural errors, extraction errors, and calculation errors. Across all models, calculation errors rate dominate, showing that LLMs frequently fail at multi-step arithmetic and domain-specific numerical rules. At the same time, structural errors remains substantial, indicating difficulties in correctly interpreting XBRL hierarchies. Together, these results explain the low accuracy we saw earlier and highlight the reliable numerical auditing requires both structural understanding and precise computation, which correct LLMs still lack. Finally, to conclude, we introduce FinAuditing, the first benchmark designed to evaluate LLMs on structured, hierarchical and taxonomy-driven financial multi-document auditing using real-world XBRL filings. We define three complementary tasks to systematically access semantic consistency, relational understanding, and multi-step mathematical reasoning. Our extensive zero-shot evaluation shows that even SOTA models struggle with cross-document reasoning, structured interpretation, and taxonomy alignment, highlighting the need for LLMs with a stronger structure, grounding, and auditing-oriented reasoning capabilities. In the future, we plan to explore combining LLMs with the financial knowledge graph to better detect XBRL semantic tagging errors. The knowledge graph would encode taxonomy structure and semantic rules, while the LLM reasons over this structure to identify invalid tagging patterns and suggest the correct correct standard tax. This direction could significantly improve the robustness and consistency of automate XBRL auditings. Yeah, that's all for my presentation. Thanks, everyone.